So in summary, if we summarize the entire lecture, then we have solved for the optimal solution for W as W star, which was the optimal solution, is simply phi transpose phi inverse times phi transpose Y, where phi matrix is each of the row represents phi xi transpose. So the first row is phi x1 transpose. The ith row is phi xi transpose. And the last row is phi of xm transpose. And this vector y is a vector of target values. So y is a vector of all the target values. So the first value is y1, the ith row is yi, and the last row is ym. So we derived this equation in the last part of the lecture, and now we are going to show you a different way to derive derive the same solution. So we have a cost function of the loss function as loss function of the data is simply sum or all I equal to 1 to m W transpose times phi of xi minus yi square. So using this matrix notation and this vector notation, we can rewrite this loss function as is phi times W minus y transpose times phi times W minus y, which is the L2 norm of phi of W minus y squared. So you can convince yourself that if you do this multiplication, right, you'll arrive at the same loss function. And here we can represent this vector. So here we have just used this, right, x for a vector z transpose z is simply L2 norm of z squared, where we are using this norm. So what is the norm? So a pth norm of a vector z is simply written as sum or all I, where z belongs to Rn, is an n-dimensional real vector, is sum or all I equal to 1 to n, absolute value of the ith component of z to the power p to this whole to the power 1 over p. So this is the pth norm of an n-dimensional vector z. So likewise, the L2 norm of a vector z would be sum or I equal to 1 to n zi square and square root of the whole thing. So if we take the square, then we get this whole square. So the L2 norm is squared of z is simply sum or all I equal to 1 to n zi square, which is nothing but z transpose z. So using this, we can just rewrite this as simply phi times w minus y. The L2 norm of this is squared. So in the matrix notation, our loss function over the data parameterized by the parameter learnable parameter w is simply phi times w minus y transpose times phi times w minus y. Right. So we can set the derivative of this function with respect to the learnable parameter w to 0. To get the optimal solution w star. So this gives us w transpose times phi transpose times phi times w minus w transpose times phi transpose times y minus y transpose times phi of w plus y transpose times y, and set it to 0, this derivative. So we just compute the derivative. So phi transpose phi is a symmetric matrix. This is an n by n symmetric matrix. So the derivative of this term, we can just write it d by dw of w transpose phi transpose phi times w minus twice of derivative of w transpose times phi transpose times y plus derivative of y transpose times y is equal to 0. So since y doesn't depend on w, so the derivative of this is 0. So we get twice of phi transpose times phi w minus twice of phi transpose times y is equal to 0. So here we have, since phi transpose phi is a symmetric matrix, so we have just used this rule that Z transpose A Z, where A is a symmetric matrix, is simply twice of A of Z. Sorry for the space. This is simply twice of A of Z. So this is what we have done over here, and the derivative of W transpose times phi transpose times Y with respect to W is simply Y transpose times Y. So by setting this derivative to 0, we get effectively phi transpose times phi times W is phi transpose times Y. So we arrived at the same equation at which we arrived earlier, and again by inverting phi transpose phi, we get a solution. W star is simply phi transpose times phi inverse times phi transpose W. Sorry, Y. So this is the optimal solution that gives us an optimal mapping function to explain the data with respect to the square loss function.